Welcome to the second in our series of conversations on quantum reality. In the first part, with Elise Carroll, we reviewed the essential conception at the heart of quantum mechanics, which is that the theory is probabilistic in its pronouncements. That is, whereas Newtonian mechanics takes as input the state of the world right now, and as output predicts the state of the world tomorrow, quantum mechanics takes as input the state of the world right now, but by contrast, predicts the probability that the world will be one way or another tomorrow. In a sense, then, reality kind of hovers in an unfamiliar, ghostly mixture of many possible dispositions. Particle here and particle there. Particle spinning this way and spinning that way, and so on. Possibilities captured by the so-called quantum wave function, and only upon some notion of observation or interaction does the world transition into the single definite reality of common experience. The previous range of possible outcomes, each provided by quantum mechanics with a particular probability for happening, seemingly collapses to one and only one definite reality. Now, how that transition actually happens, the so-called quantum measurement problem, that remains an unsettled question that to this day inspires creative theorizing and heated debate. Now, the probabilistic nature of quantum mechanics famously troubled Albert Einstein, but actually, it was another quality of quantum physics, a quality that Erwin Schrödinger identified as the feature of quantum physics, distinguishing it from the previous classical approach called quantum entanglement. That is what really troubled Einstein the most. You see, we are used to a world that is local in the sense that what you do right here affects things right here. Or if you allow your influence sometime to spread, then it can affect things increasingly farther away. But quantum entanglement shows by contrast that there are situations in what you do right here can instantaneously affect something far away. In particular, it can cause a distant object to snap out of the quantum haze of many possibilities and assume a definite disposition. Now, such non-locality, it's contrary to everything that we experience, but it seems to be an integral part of quantum reality. And as we discussed in part one, this entanglement can not only link objects far apart in space, but also far apart in time. All right, that was part one. Let's now continue with my second conversation in this quantum reality series. This is with physicist John Carroll, and he is one of the strong proponents of Hugh Everett's 1957 proposal called the Many Worlds Approach to Quantum Physics, which, as we shall see, will give us insight into the quantum measurement problem and possibly even into this issue of non-locality with quantum entanglement. All right, let's go. John Carroll is the Homewood Professor of Natural Philosophy at Johns Hopkins University and an external professor at the Santa Fe Institute. He is a best-selling author about the foundations of quantum mechanics, as well as the host of the podcast Mindscape.
Hey, Brian.
All right, so you may have heard a little bit of our conversation with Elise, and I just want to jump right off from there and trying to get your thoughts on the quantum measurement problem. Then we'll look at one or two possible solutions, focusing upon the one that you think does the best job. But how important is this measurement problem, and how would you even frame the problem?
Actually, before I even answer the question,
Please, yeah.
It occurred to me while I was listening to you and Elise, you've picked people for this program who care deeply about the foundations of quantum mechanics, which makes perfect sense. An hour from now, there'll be another program featuring the great minds of string theory. I would love to know what they think about the importance of foundations of quantum mechanics.
Well, actually, it is an interesting question because I think, as you know, many physicists don't talk about the foundations of quantum mechanics. And you're right, it could be somewhat misleading to have a program where people care about this issue. So why is it that it isn't something that's grabbed the community perhaps as fully as we think it should?
You know, I think that we all agree that quantum mechanics is super duper important to our understanding of the universe. It's the best, deepest understanding. It's the framework in which we have to work. But you can get by making predictions and fitting data without digging too deeply into the foundations. And I think that physicists are fundamentally pragmatic people, right? And I think that throughout the 20th century, the attitude was it's hard to see how to make progress on this problem. It's hard to say, let's build a particle accelerator and solve the measurement problem, right? So they tackled other problems, but I don't want to push this too far, but I think that there's a point where in fundamental physics, we have very difficult problems that we're stuck on right now. And I would argue that maybe that's because we don't understand quantum mechanics perfectly well.
Yeah. Now, there's been a lore or a phrase that is often bandied about by those who don't have any interest in, say, pursuing the measurement problem, which is basically shut up and calculate is the approach. Just use the mathematics of quantum mechanics, make your probabilistic predictions, go out and test them in the laboratory. If it says the electron 30% here, 70% here of the time, you should find it here roughly 30% of the time and here 70% of the time, and you do. And for some, that would be enough. But for you, clearly it's not. And for me, it's not either. But what then drives you to dig deeper?
Yeah, I've noticed that these folks are actually very good at calculating, less good at shutting up. But we can all do both. I think there's room for all of it. And to me, it's this wonderful, delicious puzzle that nature has given us. Quantum mechanics is totally different than any other theory in physics. Before we had quantum mechanics, there was, as you mentioned at the start, this paradigm handed down by Isaac Newton. There's stuff, there's bottles and tables and baseballs, and then we have equations that say how that stuff evolves with time. And that was it. You had those two ingredients, and maybe it's electromagnetism or gravity or whatever, those two ingredients. Quantum mechanics comes along, and you have those two ingredients still. You have the wave function. That's what replaces bottles and tables and things like that. And you have an equation that says how the wave function evolves, the Schrödinger equation. But then the rules don't stop. There's extra rules. And the extra rules all have to do with measurement.
Yeah.
When you measure the thing, you can't predict what it's going to be. There's a probability for getting different measurement outcomes. The wave function collapses. That is completely new in physics. And so what exactly is going on? I will go so far as to say the current textbook understanding of quantum mechanics is clearly unambiguously insufficient as a fundamental theory of physics because it says things like, when you measure the system, something happens. And if you say, what do you mean by measurement? It says, oh, we can't tell you that.
Yeah.
We got to do better than that, right?
Yeah. And so people have tried to do better than that. It's not as though everyone is just saying, we can't make any progress and throwing their hands up. People have put forward ideas. I wonder if we could just kick around a couple of those ideas. It doesn't really matter to me where to start, but how about the GRW theory, as it is called? What is that approach to trying to solve this issue?
Well, the first fundamental thing you have to ask is this wave function business. Is it a representation of a real physical thing, or is it just a tool we use to make measurement outcomes? So first, let's imagine it's real, okay? Then you have this collapse thing. Is that real? Does that really happen? Or is that just apparent? So GRW is one of a set of theories where you say the Schrödinger equation isn't always right. A typical particle will obey the Schrödinger equation for millions of years, and then spontaneously by itself it will collapse somewhere. And it would be very unlikely to see that in the case of one particle, but you have many, 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 many particles in a simple macroscopic object. So basically, something like the bottle here is kept in one location because at least one of its particles is just spontaneously collapsing and localizing all the time.
And that sort of yields a cascading effect then. Yes.
Because of entanglement.
Yep.
That particle is entangled with all the others, so we perceive this definite set of positions of stuff in the world, even though the deep down quantum theory is a little bit different.
And because there's so many particles, the odds are one of them will experience this new process that collapses its probability wave, and then down fall the dominoes.
And the
so to
great
speak.
thing is that it's experimentally testable, and the tests are ongoing.
Yeah, and so where do we stand on those tests?
It'll be ruled out soon. Don't worry. This is not the right theory, by the way. We're just being polite.
Yeah. And so maybe to cut to the chase then, what
You want the right theory?
Yeah, what is the right
Yeah.
theory then?
Well, we've already talked about, you talked about with Elise the fact that we describe a spinning electron, which you could observe to be clockwise or counterclockwise, spin up or spin down, as a superposition, right? That's one way of thinking about what wave functions in quantum mechanics are, superpositions of possible measurement outcomes.
A blending of the possible outcomes. so to
That's
speak.
right.
Yeah.
And so the measurement problem arises because when we look at the electron, not only do we never see it in a superposition, but we've never felt like we are in a superposition of seeing anything at all, right? So we invent all of the superstructure of collapses and measurements and ill-posed parts of our fundamental physical theories. So Hugh Everett, who's a graduate student at the time, said, what if we just don't do that? What if we just say we have a wave function, and not only the electron has a wave function, but you and I are part of the wave function of the universe, and we just ask what would be predicted by the Schrödinger equation if we went back to the classical paradigm where we just have stuff and an equation?
Yeah.
What would happen? And the answer is that that part of the wave function, let's say, that has the electrons spin up and spin down, it doesn't disappear when you do a measurement. A measurement is clearly defined in this picture as a physical interaction between the observer and the system, and the decoherence part is also important. And what happens is you end up in a superposition of the electron was spin up and I saw it spin up, plus the electron was spin down and I saw it spin down. And Everett's entire contribution was to say, and that's okay.
And take that seriously.
Yeah, take it seriously, because Niels Bohr would have said, but it looks like I'm now in a superposition of having seen the electron spin up and having seen it spin down. And Everett says, and they literally had this conversation, you've misidentified yourself in the wave function of the universe. You are not the superposition of those two people. You are one or the other. There is now a person who saw the electron spin up. There's a different person who saw it spin down. In fact, there are two whole different universes, which we now call the many worlds.
But those two people have the same memories up until that point.
They have the same pasts and memories and potentially different futures. If they decided whether or not to get married on the basis of that quantum measurement, they could have very different futures.
Yes.
I don't know, did I rub something
No,
wrong?
you just did bring a lot of thoughts to mind there. Yeah.
Did you do a Stern-Gerlach experiment?
Not just it's an interference between the other universe. We spoke about that. But so let's just see a little
They're
visual.
very unhappy. The other Brian.
Yeah, I'm so glad I'm not that one. So we have a little visual. If you can bring up the dart, just as a prototype of the process. So imagine throwing a dart at a dartboard. We all experience the dart hitting the board. But if you can do the many worlds version of this, so this thing is going forward, and then the dartboard splits, say, into 9 possibilities. The dart experiences 9 realities, and if I'm watching the dart, I am experiencing one of those, but there are 8 other of me who are experiencing the others. Now, clearly, this seems nuts.
Yeah, because quantum mechanics. That's why. The point is that if you believe in quantum mechanics at all, you will describe the dart as possibly being in a superposition of hitting in all these different possibilities. All many worlds says is, yeah, that's the world. That's what it is. If you can believe that an electron can be in a superposition of spin up and spin down, it doesn't require any more intellectual work to say the universe can be in a superposition of I've measured it spin up and I've measured it spin down and so forth. Hugh Everett did not put in a bunch of worlds. The wave function put in a bunch of worlds. He just says, it's fine, deal with it.
And just take the mathematics at face value, in essence.
It's the leanest and meanest version of quantum mechanics.
For sure.
It's just there's a wave function and an equation. Everything else pops out, or hopefully pops out. There's still work to be done.
Now, there is an issue with this picture. If you could bring the dartboard back up. We have a theory that supposedly is rooted in probabilities.
Yeah.
Which says that one outcome is unlikely, another outcome is likely. But in this many worlds approach, every outcome is happening. And so if every outcome is happening, how can you ever say that one of those outcomes was unlikely?
Good. I think that this actually is, I say good, I'm sorry if I sounded ironic, but it actually is the right question to ask about many worlds, because it's a deterministic theory. The wave function of the universe just obeys a simple equation. We know exactly what it's going to look like. One person saw the bullseye, et cetera, et cetera. And in what's happening is we need to change our notion, depending on what your notion was, but potentially change our notion of what probability means. Because there is a moment in the history of the universe, in that dartboard example, where the universe is split into 9 possibilities, but you, the thrower of the dart, does not know which of the 9 possibilities you're in. So there are 9 of you. You don't know which one you are. And what you're supposed to do in that situation is to assign a probability in your mind. What do I think is likely for the question, which universe am I in?
Like before I open my eyes kind of thing.
Yeah, and the thing is, you don't need to wait, because the splitting of the universe happens so fast that there will always be time. And so it sounds a little different than we're used to, because it's kind of subjective. It's not a frequency of anything. But if you stick to the program and say, like, what would a sensible, rational person do in that situation of uncertainty, there turns out to be a uniquely right thing to do, and that thing derives exactly the thing that is postulated by other approaches to quantum mechanics, that the probability is the wave function squared.
And so you're convinced that this works, and you're convinced that this is actually how the world really behaves. This is not expediency. This is what you feel in your bones.
I'm convinced is always too strong, right, in science. I'm always willing to change my mind. If a better theory comes along, if the GRW collapses are found experimentally, I will change my mind like that. Everett will be falsified, and we will move on. But I think that, when you have a theory whose fundamental ingredients are so simple, one that fits the data so nicely, I'm not going to spend my time thinking about other theories. I'm going to put that theory to work, because I think that exactly for what you said at the start here, which is that physics has ignored this problem for many, many decades now. There are foundational questions to be asked connecting the wave function of many worlds quantum mechanics to the reality of our world, potentially in ways that are quite illuminating for existing puzzles in physics. So I'm not necessarily convinced of it, but I'm sufficiently optimistic about it that my program is developing that theory, not worrying about other people's theories.
Yeah. Now, in the conversation with Elise, toward the end, we began to think about quantum mechanics and its implications for the fabric, the nature of space-time itself. This is an issue that you spend some time thinking about as well. So what illumination does quantum mechanics or many worlds give to your picture of what space-time is?
I mean, that's a great question, because it's a little misleading to even think about many worlds as many worlds, right? Like Everett didn't put in a bunch of worlds. It's the theory of the wave function just obeying the Schrödinger equation. And it's one possible theory. There's other options. And in physics, we have puzzles like gravity, right? Like quantum gravity, that string theory is purportedly a theory of, as well as other theories. The other parts of nature that we know from experiment, the matter particles, electromagnetism, the nuclear forces, we've done a very good job in what we call quantizing them. That is to say, we start with a classical theory, and then we have a cookbook for turning this classical theory into a quantum theory. But there's no guarantee that works. There's no unique way of constructing every possible quantum mechanical theory from a pre-existing classical theory. Nature doesn't do that. Nature just starts quantum from the start, right? And guess what? When it comes to gravity, we have a very good classical theory. You try to apply the rules to it, do the cookbook, and it doesn't work.
Sure.
We had no right to expect that it would work. I think that it's very possible we just got lucky with the other forces. And in the case of gravity, maybe the fact that it's hard for us to understand quantum gravity is related to the fact that we don't understand quantum mechanics. And taking things from the Everettian wave function first point of view suggests different ways of making progress on that. Suggests that what we need to do is think about why something as abstract and mathematical as a wave function would ever look like space-time in the first place. And what you find is that when you start sort of nibbling at that question, you get a kind of description of space-time that seems to have gravity in it. It's kind of a natural thing. And this is a very, speculative, early kind of program, but I think that given the importance of quantum mechanics to the whole picture, it's a very, very intriguing path forward.
And so you rightly describe, historically speaking, that when we were talking about the electromagnetic force, it began with Maxwell thinking in a very classical manner, by classical following in Newton's footsteps, where in describing the electromagnetic force, Maxwell used the language of where things are, the strength of the field at that location, how quickly the field is undulating at that location, all ideas that we can picture. We can make an analogy to water waves. I mean, it's a very classical way of describing things. And when quantum mechanics came along, we were able to put Maxwell's ideas through this sort of quantum mechanical conveyor belt and reframe it in a quantum mechanical manner. Why is gravity different? I mean, you say we just got lucky with, say, the electromagnetic force or the strong and the weak nuclear forces. Where did that luck come from? Do you have a sense of what makes those forces amenable to this approach and gravity not amenable?
This is a suspiciously good question that I haven't actually prepared a potted answer to. This is like, I'm sad now, but there's an obvious suggested answer, which is that gravity, going back to what Einstein hit on when he invented general relativity, gravity isn't quite a force propagating in space-time like the other forces are.
Yeah.
It's a feature of space-time itself that makes it special right out of the box, right? And so if you're a true hardcore austere Everettian, what exists is something called the quantum state, which has a mathematical description that John von Neumann and others have figured out, and it's a vector, and you can learn linear algebra, it's full employment, it's great, but space is not there. Right? Space is not part of that fundamental quantum description. It has to emerge out. And so I think that what is special about gravity is the way in which we extract the classical world from the quantum wave function has special gravity parts built in, right? Like gravity plays a slightly different role, even in ordinary physics. So I don't think we should be surprised that it's a little bit different in quantum mechanics either.
Yeah. Can we spend just a few minutes talking a little bit about entanglement, as that was something that we spoke about with Elise, and is certainly a key feature of quantum mechanics, because, as I think many people know, the Nobel Prize in Physics, was not long ago, 2022, awarded to three folks whose real impact was in the arena of entanglement. And you pointed out to me, and I hadn't even noticed it myself, that the Nobel Prize citation was actually a little bit misleading, and it relates to this question of the measurement problem. We sort of have it here. So the citation says that the Nobel Prize was for work whose impact was to show that quantum mechanics cannot be replaced by a theory that uses hidden variables. And as this is an idea which is one other approach to solving the measurement problem, what are hidden variables and why is that wrong?
There's a very juicy story that I can't resist telling here, but if I go on too long, you'll cut me off.
Please, go for it.
So David Bohm was a graduate student of Oppenheimer in the 1940s. He was forbidden from working on the Manhattan Project because he was suspected of communist sympathies because he totally had communist sympathies. But after the war, he became an assistant professor at Princeton. He made a classic assistant professor mistake. He wrote a textbook about quantum mechanics. And in the textbook, he says this idea of hidden variables had been around. It's basically if you have a wave function that is a wave, but then when you look at the electron, it looks like a particle, well, one very natural approach to take is there's both waves and particles, right? The Everettian says there's just the wave, but it looks like particles because of physics. The hidden variable folks would say they're both, and what you're seeing are the particles.
Yeah, and he wrote it up both in a textbook, but also in a paper as well.
But no, 52. In the textbook, he said you
because
can't
of the conversation
do
with Einstein.
Exactly.
Yes,
so in 1950, he writes a textbook. He says, as we all know, John von Neumann has proven a theorem that says hidden variable theories can't be done. Of course, von Neumann's proof was in his textbook, which was in German, that Bohm hadn't read. No Americans had read it, and they weren't that interested in the foundations of quantum mechanics anyway. Fortunately, at Princeton, there was a guy who spoke German who was very interested in the foundations of quantum mechanics, Albert Einstein. Einstein summons Bohm into his office. Bohm was like, nope, sorry, can't make it. No, he went there to talk to Einstein, and Einstein says, look at what von Neumann says. It doesn't actually prove what you said. So, and Bohm was super smart, and he went and said, you're right. Let me see if I can write down a theory with hidden variables. And he did, and it fit the data, and it was all kind of nice.
And then, just to be clear, so hidden variables is, even though the probability wave says, say, the electron is like spinning up, partly spinning down, partly, it's really spinning up or spinning down. It's just quantum mechanics has not given you that hidden information.
That's right. There's a fact of the matter, which will be revealed by the measurement, which we don't know ahead of time. That's completely different than the pure wave function approach that you would get in Everett or in GRW, for that matter. There's something extra there. But there was a suspicious feature of Bohm's approach, his theory, which is non-locality. That somehow what the particles are doing here has an effect on what the particles do over there. You can't use it as a telephone or anything like that, but it's there, and that helps explain the entanglement experiments. So he wrote a paper, Bohmian mechanics, it's currently known. Nobody cared. It's foundations of quantum mechanics. One person who cared was John Bell. And when I said nobody cared, but then someone cared, Bell didn't tell anyone he cared. He was a standard particle physicist working at CERN at the big particle physics laboratory.
And you probably want to hide that you care.
He did. On weekends and vacations, he would work on this. And he asked himself, he said, this is very interesting. Because at the time, there's a lot of people who thought that thinking about things collapsed the wave function, right? Like consciousness played a role, and that seemed very spooky. And so Bell said, look, this theory is very mechanistic. It's what we want out of a physics theory, but it has this non-locality in it. Bell went to his grave saying that we should teach Bohmian mechanics sophomore year to undergraduates, because it's a very definite theory. And he asked himself, this non-locality, it bugs me. Is it necessary? Is it possible to get around the non-locality and still have a hidden variable theory or something like that? He proved a theorem that you can't do it. You will always have that non-locality in there, the Bell inequalities. No one cared. Until, these days, we do have a little bit of an upswing in the foundations of quantum mechanics. In the physics community, we did experiments, the royal we did experiments, Osprey, Clauser, Zeilinger did these experiments that showed that Bell was right. They verified his inequality. And then the Nobel Committee says, now we've ruled out hidden variable theories. Even though Bell was a huge fan of hidden variable theories, because even very, very good physicists don't know this story. They don't know that non-local hidden variables are still viable. They're not right, but they're viable. And so it's
So, John, I know that's a little flippant. Just to clarify, when Sean says he doesn't think they're right, but it's a viable approach that particles could have definite features, something that we think is not the case when we ordinarily have an intuition about quantum mechanics. They could have definite features, but if they do, there's a manifest non-locality that theory has incorporated within it.
That's right. One of the reasons why I am being flippant and I don't think that it's right is that it's difficult to make this approach play well with modern quantum field theory. So but of course, I'm a huge supporter of people trying to do research on these ideas, whether it's spontaneous collapse or hidden variables or even wilder ideas, because as much as I personally have something I'm choosing to do research on, we don't know the final answers. And when I'm in my more sober modes, I'm going to tell you that we want to make all the research programs move forward.
So one final question. What do you think the time scale is and to get these in? I mean, because you look, Elise mentioned, 2025 is the 100th anniversary of quantum mechanics. You could date it even further back. You can date it to 1900 with Planck or 1905 with Einstein. But, it's on the order of a century that we've been using this theory to make the most precise predictions in the history of science, and they are confirmed through exquisite experiment. They all work, and yet here we are still arguing about what it all really means for the nature of reality. Is this ultimately soluble, Or is it that our brains are searching for a kind of intuition that the universe just isn't set up to provide?
You know, I think that there is something that is completely acceptable and sensible to me about the fact that we don't agree. Because the fundamental quantum problem is that it separates out how we talk about systems when we're not observing them from the measurement outcomes, then there's kind of two different ways to go. You either say that way that we discuss the system when we're not measuring it, wave functions, Schrödinger equation, that's the fundamental thing, and I'm going to have to tell a story about measurement outcomes. That's what Everett would have to do.
Yeah.
But there's another way of going, which is, look, measurement outcomes, that's what I see in the world. That's what I care about, that's reality. I'm going to tell a story about why the wave function works so well when I'm not doing measurement outcomes. And it's perfectly acceptable to go, that's a question of intuition and taste, right? Because we don't know the final answers yet. But also, I would say we haven't been sending our best. We haven't been putting our complete effort into it. You know, I joke about the fact that if you told an outsider that physicists have this really important theory that is at the foundations of everything they do, but there's this looming question at the heart of it, they would say, oh, well, the people who work on that theory must be the superstars of physics who are fought over by the best universities with superstar salaries thrown at them. And you and I know, no, you're actually fired if you work on that. But maybe that will change.
Maybe that will change. Please join me in thanking Sean Carroll.
Thank you.
While it is surely hard for me, and I suspect most people, to really embrace a world that is one of many worlds, containing many versions of each of us, experiencing many versions of reality, this approach does provide the mathematically leanest and most economical interpretation of the foundational equation of quantum mechanics. Again, look, it's important to remind ourselves over and over again, if necessary, that our intuitions, our predilections for how we assess reality, they have been shaped by hundreds of thousands of years of evolutionary history in which the focus was on successfully navigating the everyday world. And that formative goal is oblique to the far more recent goal of understanding the true nature of reality. So perhaps we should expect that when confronted with the true nature of reality, our intuition will not be prepared to easily accept it. Now look, this doesn't by any means establish that the many worlds approach to quantum mechanics is right, but it does make clear that our inclination to resist such a strange idea is by no means evidence that it is wrong. Okay, in the third part of this quantum reality series of conversations, we will push these ideas farther still with physicist and author Carlo Rovelli. Join me there.